Retinal vessel segmentation is a promising method for diagnosing various diseases, including neurological disorders, by analyzing the unique structure of the retina. The retina provides a direct in vivo window into neurological health, and specific structural changes in retinal vessels can serve as early indicators of diseases. This work presents a lightweight retinal vessel segmentation network based on the encoder-decoder mechanism with region-guided attention. The network introduces inverse addition attention blocks with region-guided attention to focus on the foreground regions and improve the segmentation of regions of interest. To further boost the model's performance on retinal vessel segmentation, a weighted dice loss is employed, which is effective in addressing class imbalance issues frequently encountered in retinal vessel segmentation tasks. Dice loss penalizes false positives and false negatives equally, encouraging the model to generate more accurate segmentation with improved object boundary delineation and reduced fragmentation. Extensive experiments on a benchmark dataset show better performance compared to state-of-the-art methods, with a recall of 0.8285, precision of 0.8098, accuracy of 0.9677, and F1 score of 0.8166. This paper introduces a lightweight retinal vessel segmentation network, leveraging an encoder-decoder mechanism with region-guided attention. The authors incorporate depthwise separable convolutions in both encoder and decoder blocks to minimize computational complexity and enhance model efficiency. By reducing the number of filters in these blocks, the model's robustness is increased. Weighted dice loss is employed to improve model performance on retinal vessel segmentation, effectively addressing class imbalance issues common in this task. Inverse addition attention (IAA) blocks are introduced to focus on foreground regions and improve the segmentation of the region of interest (ROI). Key contributions include a lightweight region-guided segmentation network with only 40K parameters, suitable for deployment on devices with limited resources. Region-guided inverse addition attention blocks and weighted dice loss tailored for retinal vessel segmentation. Partial decoder and multiple attention blocks aligning high and low-level features. And extensive experiments to identify optimal hyperparameters for retinal vessel segmentation on benchmark datasets. The text delves into the realm of medical image segmentation, particularly focusing on retinal vessels. It highlights the limitations of traditional convolutional layers in capturing complex vessel structures and introduces deformable convolutional networks as a solution. The concept of lightweight models is also explored, emphasizing the need for efficient networks that can operate on devices with limited computational resources. The region-guided attention network is proposed, which uses a modified U-net architecture and an inverse addition attention mechanism to enhance segmentation performance while maintaining computational efficiency. The encoder block of this network is detailed, featuring depthwise separable convolutions, batch normalization, ReLU activations, and max pooling to achieve efficient feature extraction. Image segmentation is enhanced through the incorporation of novel blocks into the network architecture. The ground truth block is modified by adding a sigmoid function and inverse elementwise multiplication, where x is subtracted by 255. This adjustment enables the model to focus more intensely on foreground pixels. The decoder block, comprising a deconvolution operation followed by depthwise separable convolution, upsamples input feature maps and refines them through convolutional layers and ReLU activation. Spatial information is preserved through the use of skip connections. To further emphasize vessel regions, the inverse addition attention block is implemented, suppressing background information. This structured approach progressively refines the model's attention on vessels, thereby enhancing segmentation performance. The proposed network architecture aims to enhance segmentation accuracy by preserving spatial details and improving feature representation. It begins with the input SHIN, which is processed through encoder blocks consisting of convolutional blocks, batch normalization, and max pooling. Each convolutional block, defined by equation 1, includes a separable convolution, batch normalization, and ReLU activation. The output of each encoder block is fed into the next, with the final output passed to the bottleneck layer. The bottleneck layer output is upsampled and concatenated with the previous encoder block's output, then passed through another convolutional block. This process is repeated for decoder blocks, with each output concatenated with the previous block's output. The final decoder block output is passed through a partial decoder to aggregate high-level features. An attention mechanism, IAA, refines the features for more accurate segmentation. The attention block operates on the decoder output, generating a predicted segmentation mask refined through inverse addition blocks. The final predicted mask is obtained by passing the refined mask through a 1x1 convolutional layer followed by sigmoid activation. The network is evaluated on 3 datasets: drive, chase_db1, and stare, with augmentations including resizing, flips, and 360-degree rotation. In the realm of medical image segmentation, the U-Net architecture has been a cornerstone for researchers. This study delves into the impact of different loss functions and filter counts on segmentation performance. The findings, as presented in Table 2, reveal that employing the dice loss function in conjunction with fewer filters in both the encoder and decoder blocks yields optimal results. The integration of a region-guided attention mechanism and a cascaded partial decoder further amplifies the performance. This underscores the efficacy of the dice loss function in mitigating class imbalance, a common challenge in medical image analysis. Moreover, it emphasizes the importance of striking a balance between global and local contexts to achieve accurate segmentation. These results suggest that judicious selection of loss functions and network components can significantly enhance segmentation performance. This insight is particularly pertinent for researchers working on improving the precision of medical image analysis, where accurate segmentation is crucial for diagnostic and therapeutic purposes. The paper introduces a groundbreaking lightweight segmentation network for retinal vessel segmentation, showcasing superior performance on the drive, chase, and stare datasets. Despite its compact size, with only 0.04 million learnable parameters, this model outperforms existing models by effectively addressing class imbalance issues. The proposed method leverages an encoder-decoder mechanism, partial encoder, and inverse addition attention blocks to accurately capture both thick and thin retinal vessels. This approach is computationally efficient, making it suitable for devices with limited memory and resources. A qualitative analysis of the model's performance on sample query images from the drive dataset is also provided. This work significantly contributes to the advancement of medical image processing and holds potential applications in the field of ophthalmology. In this study, we present a comprehensive investigation on region-guided segmentation for retinal vessels, complemented by an in-depth ablation study centered around hyperparameter optimization. A pivotal component of our approach is the region-guided attention network block, which focuses on foreground pushing. Furthermore, the cascaded partial decoder aligns high and low-level features, leading to a notable 2.7% performance enhancement. This research offers significant insights for researchers, providing a robust foundation for improving retinal vessel segmentation without the necessity for extensive hyperparameter optimization, thereby accelerating future research endeavors in this field. The final page of the research paper reviews recent advancements in retinal vessel segmentation, focusing on deep learning models and their applications. It highlights the work by Wu et al., who introduced VesselNet, a multipath supervision model for retinal vessel segmentation, and their subsequent improvements. The authors also discuss the SegNet model proposed by Badrinarayanan et al., a deep convolutional encoder-decoder architecture for image segmentation. Furthermore, they mention the WaveNet model developed by Liu et al., a lightweight deep network designed for retinal vessel segmentation from fundus images.